Viewers treat screens as passive slabs of glass with pixel counts, but the reality is a war zone of atomic physics where manufacturers fight entropy and heat to force light out of matter. While spec sheets compare brightness and nits, the real battle happens at the quantum level. How do we trap single atoms or manipulate electron states without melting the circuitry? This video explores why impossible displays bendable OLEDs that last years or micro-LEDs with infinite contrast are not just marketing terms, but victories over fundamental physical laws. We are hacking light emission by isolating materials from their environment and forcing them into quantum states they would naturally reject, turning the screen into a controlled laboratory rather than just an image generator. The common misconception is that modern screens are simply glass panels with tiny lights behind them, stable and reliable components we can buy off the shelf. This view ignores the fundamental instability of manufactured matter at this scale. In traditional electronics, engineers often rely on mechanical oscillators like pendulums or quartz crystals to maintain timing signals. These components drift and degrade over time because no two manufactured parts are exactly alike. A quartz crystal might vibrate slightly faster than its neighbor due to microscopic imperfections in the cut, leading to frequency errors that compound into system failures. This is a problem of mechanical variance. Even with perfect manufacturing, thermal expansion causes materials to change shape and properties as they heat up during operation. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To achieve high-performance screens that do not degrade, engineers had to abandon reliance on manufactured consistency and instead leverage the purest beats in the universe found within atoms themselves. Atoms are identical by nature. A carbon atom in a screen is exactly like every other carbon atom in existence. It does not suffer from manufacturing drift or wear out because of microscopic scratches. The engineering challenge becomes one of isolation rather than assembly. To create stable light emission, manufacturers must isolate specific atomic structures from their environment to prevent thermal degradation that would otherwise scramble these delicate states. This process involves bombarding these isolated atoms with light waves tuned precisely to a resonant frequency. When resonance occurs, electrons absorb energy and undergo a quantum jump, shifting between distinct internal energy states without the material physically breaking or degrading over time. This level of precision allows for frequency measurements with more than double the accuracy of conventional methods used in older display technologies. It enables the creation of superposition states where a particle exists in multiple vibration levels simultaneously, reaching up to 100 quanta of motion per flip. In practical terms, this translates to materials that can maintain structural integrity under extreme stress. When you bend a flexible phone screen, you are not just stretching plastic, you are relying on engineered atomic traps that allow electrons to shift states without snapping the circuit's physical bonds. The underlying atomic lattice is being actively stabilized against thermal noise, effectively turning the display into an active quantum system rather than a passive light source. However, this engineering feat comes with significant physical limits regarding heat and power density. Recent breakthroughs in quantum control demonstrate that it is possible to trap single ions such as beryllium within electromagnetic traps cooled near absolute zero. By using precisely timed ultraviolet laser pulses, engineers can flip the internal spin states of these atoms, adding exactly 1 quantum of motion per flip. This level of precision allows for frequency measurements with more than double the accuracy of conventional methods and enables the creation of superposition states where a particle exists in multiple vibration levels simultaneously up to 100 quanta. In display manufacturing, this translates to materials that can maintain structural integrity under extreme stress, allowing screens to bend or flex without breaking circuitry because the underlying atomic lattice is being actively stabilized against thermal noise. The viewer learns that impossible specs like infinite contrast and zero degradation are actually engineering feats where physics is being hacked at the subatomic level. This explains why a $2,000 micro-LED TV lasts for decades, while an OLED screen degrades in months. It is not just about better pixels, but how well the manufacturer controls the quantum state of the light-emitting material to resist heat and entropy. The difference lies in whether the system can maintain that delicate balance between energy absorption and structural stability under continuous operation without succumbing to thermal runaway or atomic drift. Achieving these specs requires cooling systems near absolute zero in labs or highly complex fabrication to mimic those conditions at scale for consumers. We must remember that while 2/3 of the universe is attributed to dark energy and about 1/4 consists of dark matter, our struggle here is with the very small scales where light and matter interact. The future of displays depends on mastering these interactions, not just in theory, but through mass manufacturing processes that can replicate quantum stability without requiring a laboratory environment for every single pixel. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.